Hello, I'm Edward Berman, and I'm going to be talking to you about the central limit theorem. I'm going to give you the context, state the theorem, its interpretation and significance, go through an example that is helpful for understanding, make connections, and share the proof. So, for some context, we keep seeing this bell curve shape in nature. We aim to answer both why the shape is so common and understand the connection between discrete independent events and continuous random variables. So the theorem states the following. For an infinite sequence of random variables such that e of xi equals mu, and the variance of x equals sigma squared, where mu and sigma are finite, then we have the limit as n goes to infinity, the probability that the sum of these random variables up to n minus mu n over square root n sigma is between a and b is equal to the integral from a to b of this function, which is a Gaussian. So consider a series of independent events. We add them all up, and we surpass the mean and divide by the variance of all the events, which gives us this denominator. Uh, and we take an arbitrary number of indicator variables. You can call it, the samples, indicator variables, whichever is more suitable for you. This will give us an approximately normal distribution, and as n goes to infinity, it becomes a normal distribution. This explains why the bell curve appears so often in nature. That is, making a claim about how a series of discrete random variables converges to a continuous random variable, we're able to understand why so many seemingly different phenomena have the same distribution. It is because all of these different phenomena arise from a series of independent indicator variables. These indicators form a binomial, which become a normal under the appropriate limits. So as an example, I have an arbitrary number of walkers, maybe like they're particles that start in the center of a pool and they can drift through the water left or right. The classic example is falling of water. Uh, Brownian motion might be a term you're familiar with. Let's say we start at the origin. At every time step t, they have some probability of moving to the right and some probability of moving to the left. According to the central limit theorem, if we measure their distribution along the number line after some time, we will see them normally distributed. And one thing like to connect to is the moment generating function, which is helpful in proving it. Uh, it has this form, the expected value of e to the tx, and if we take a Taylor expansion, we will know that the jth derivative of this function at 0 gives us the jth moment of the function, hence its name. So now we're going to prove the central limit theorem. Let x1, x2, all the way to xn be a sequence of independent random variables having mean 0 and variance sigma squared. So notice this is already a little bit of a weaker version of some other proofs because we are making some sort of big assumptions. And the common distribution function f and moment generating function m defined in a neighborhood of 0. So we're going to find some terms. Sn is the sum of these independent random variables, and Zn is this sum divided by sigma square root n. We're going to take advantage of this fact about moment generating function. At the moment generating function of x is y, it's exponential. We see this nice property we're adding here turns into multiplication here. The moment generating function of each random variable xi is the same. So x plus x plus x, that's the same as x to the n. So we can say the following. The moment generating function of Sn of t is equal to m of t to the n, and we say something similar for m of the n. So now we consider a Taylor series of the moment generating function of t over sigma root n and let epsilon of s denote higher order terms. This comes out to be this, and therefore going from this to the moment generating of dn, we get something that looks like this if we square this and do some algebra. So now let's consider the limit. As n goes to infinity, this epsilon n goes to 0. Additionally, if we let a and b equal t squared over 2n, this looks a lot like e to the a. So it follows that where a is this, so it follows that as n goes to the infinity, moment generating function is e to the t squared over 2. Observe that this is the moment generating function of the standard normal. So our summation of independent events must have converged to standard normal for the moment generating function to take this form. And that is our proof of the central limit theorem.